Hello everybody, I'd like to continue on my work to get a system in resonance. We had done what we have done the last time is we have individually tuned coils, primary, secondary coils to the resonant frequency we did choose at that time. That was 1.35 megahertz. However, that is only valid if you work in a one-to-one relationship. That means one primary, one secondary. Then this kind of calculation would then be efficient to have a running system. However, here we have literally two systems we need to tune to each other. That means we have two secondaries connected to each other, and we have two primaries as well. They have all an influence. And also, from a tuning point of view, as we have seen the last time, I need to connect the system for the high voltage input to get an accurate measurement. So there is no capacitance here. I measure the frequency, measure the frequency feedback, adjust it then to the additional via resistance of system, get a measurement, and that's my calculation point for choosing the capacitance. There's an additional thing I have changed. I will have in between both coils, I will have capacitance. There will not be a direct connection, there will be capacitance. So that's going to be a change in the system. I'm gonna connect a different kind of equipment at a later stage, which should show us some interesting effects. We'll talk about that later. So our first goal here is to have a system which we can drive with high voltage. Let me go briefly through the measurement setup and instrumental setup. I use this time two probes, one on the input side and one on the output side. For the first measurement, I just connected directly to the primary coil. The second one will be including spark cap and wiring and so on. Here I have my variable capacitor connected between both secondary. So this one gives me a value for the best tuning or resonance in the system. I will take off this measurement and will apply it to the equipment I'm going to connect in between. Here nothing has changed. Here we're not connecting anything on the end side, very important. And we're connecting here directly to ground. I used the capacitor before. It made a difference. However, the capacitance is so low, I don't have any capacitor currently which can cope with it. The direct connection is the most efficient one. So let's have a look, see what we got here. I get for my input side, which is measured in between the coils, get 582 volt. On the output side I get 266 volt. So the 266 volt are coming from here. So I would expect a reduction in voltage on the secondary primary. That is the expected behavior because of the coil ratio between secondary and primary. However, it's not a one-to-one relationship, as you can see here. So we have still a lot of voltage on that system. Let me just change a bit capacitance here. You can see when I change the capacitor between them, it's highly sensitive to strict capacitance, to parasitic capacitance through my hand. As again, please remember, remove all metal equipment, any kind of equipment from the measuring side. It will have an influence on your measurement. So frequency at the moment 546. I'll go a bit up. Quite nice. Let me change to channel 1. 610, 618 volt. So that's a good value, good starting point. So we have 559 kilohertz. However, that is direct connected. Now I do a measurement connecting the whole system. I have now connected the wires of my output, my little driver, directly to spark gap and additional wire. So this will be a connectivity point then for the high voltage power supply. We're going to choose the microwave oven transformer, and we choose then the capacitance, which will be given by the measurement we're having here. So you can see the value is reduced here. So you have two possibilities. The first possibility is to change the capacitance on the inbound side. Let me show you. But it doesn't give you much of a value, so you have to change the frequency. And because it's higher resistance, I expect lower frequency. Yep, slightly lower. Let's see if I can change this capacitance. Not much. So as you can see, resistance is dampening the resonance. So that is a standard behavior in RLC network. A resistor in a network is dampening the Q, as you can see here, quite a lot. I'm losing a lot of, well, let's see, yeah, 424 for Gen 26. That's about it. For 30, it loses quite a lot of energy, and the frequency is slightly lower now as well, 548. Just in case you're curious, I have removed the capacitor. Does the same calculation to show you what that means in the system. You see here quite a large drop. Let me get this up a little bit. Okay, now I have to tune to find the frequency. So as you can see here, it's a bit more equal. Channel 1, 362, so the voltage is lower, and channel 278, but there is not a bigger difference anymore between the driving side here on channel 1 and the output side on channel 2. Frequency has changed now to 560, so it's a lower frequency, interesting enough. So you would normally expect, if you have a capacitance in between, in a series capacitance, that the frequency should drop. Here, however, it's the opposite. So we have a higher frequency with a capacitor connected between the secondary, and we have a lower resonant frequency without capacitance connected. My idea for using a capacitance between the secondary coils is a plasma dome. So the calculated capacitance would be 23.6 picofarad. However, it would mean that I have completely to close this one with various metals. I use aluminium and copper, so I could reduce it on that level to 500 kilocycles, so that's about 20, 30, 40 kilocycle higher, but that's good because it gives me, let's say, 7.5, 10, 15 nanofarad. I don't need to make any kind of adjustments anymore, so I can use this one. So interesting is here, as you can see, voltage it's almost the same or a little bit higher on channel 1. On channel 2 get a nice, well, 90 volt out from here, and that's all via dome. As you can imagine, let me show you, putting my hand here on it has a tremendous effect. Yeah. So this one, so if my calculation is correct, and I'm going to energize that now with the correct capacitance, and also very important, you have to isolate your power supply from your tank circuit. So I will attempt it as well, so that it keeps it independent. That means my capacitance will be accurate, that will be in resonance, that system, but my power supply will not have any influence of the frequency, so I have to isolate it. And the way we do that is we're using diodes, so that we have an independent resonant frequency circuit from the power supply.